So we started on this right before we got out for break. We talked about the confidence interval. We start with something called the level of confidence. Ideally, you want that as close to 100% as possible. There is a bit of a problem. If your level of confidence is exactly 100%, you you actually have issues with your interval being too wide or too, it's just so obvious. For instance, 100% confidence interval for a proportion would be, oh, well, that it's uh, over, it's between 0 and 1, which we already knew that about a proportion. Um, so lots of interesting things here. One thing I'll say is if you have a 95% level of confidence, you're going to compute something called your alpha. So if your confidence level is 95%, that's leaving 5% on the table. And thus you would say alpha is 0.05, which is 5% as a decimal. So alpha is the amount you're leaving on the table. We're also going to use that in order to figure out basically the z-score we need in our confidence interval calculation. So we have a couple of things we have to realize here. Just like in chapter 8 when we were dealing with, what's the shape of the distribution of p hat, we need n, your sample size, times p, the hypothesized value of your proportion, times 1 minus p to be greater than or equal to 10. Technically, we also need the sample size to be less than or equal to 5% of the population size, which in practice is usually not going to be a problem. But then we remember that the mean and standard deviation for our sampling distribution is p and square root p1 minus p over n. Which again, this is exactly like chapter 8. So the formulas we're using are not foreign to us. They are something we've dealt with. So finally, here's this big, beautiful formula. Suppose that a simple random sample of size n is taken from a population. A 1 minus alpha times 100% confidence interval for p is given by p hat plus or minus c alpha over 2 times p hat times 1 minus p hat all over n. So a few notes on that. That is called our margin of error, the margin of error. So whenever you see, if you're watching the news and they say we took a poll about who is going to vote for which candidate in this state, in the state of Minnesota maybe, and they say, well, 52% are voting for candidate A with a 3% margin of error. Well, a 3% margin of error in that case means that while their data said 52% of the sample would vote for the candidate, their confidence interval is actually 52 minus 3, which is 49, 52 plus 3, which is 55. Their confidence interval is actually 49% to 55%. That's the interval of values that they believe will vote for that candidate. It's kind of hard to explain, but basically, if we take a sample of a given size and compute it over and over and over again, we expect that 95% of the time, the true population proportion that we're trying to measure will fall into our confidence interval. That's really kind of the interpretation. So a 1 minus alpha times 100% confidence interval. So a 90, let's say you're talking about a 95% confidence interval. A 95% confidence interval indicates that 95% of all simple random samples of size n from the population will result in an interval that contains the parameter. Again, that's sounds like some double wording or some vague wording just for the sake of being vague. which isn't entirely true, but it is a little bit confusing when you explain it in that light. But what's really kind of the crux of this, I mean, all this is just a calculation. This right here, the z-score that we need, is kind of the crux or the hardest part when it comes to calculating a confidence interval. And it's actually not as hard as you think. If you have a 95% confidence interval, that means that within two z-scores, and these z-scores are symmetric. These two z values are symmetric. They are just opposite signs of each other. You have 95% of the data falling in between a lower and an upper z-score. That leaves 5%. That leaves 5% for the two outside pieces, or AKA the tails. So 5% falls between here and here. We divide it in half to know how much goes into each one of them. So that leaves 2.5% on each side. So that's what I'm going to put here. We're going to say, 2.5% belongs here. Put it in red for Christmas. And 2.5% belongs here. So you can look at two things. You can look at this z-score. This z-score will be negative. And it has 2.5% of the data to the left of it, or 0.025. Remember, when you're using the actual z-chart, you may need to convert to a decimal. Now this z-score over here this z-score has, well, think about it. It's got, if you're starting from here, it's got 95% of the data plus an extra 2.5% of the data if you go all the way down to the left. So it has 95 plus 2.5 equals 97.5%, or 0.975 of the data to the left of it. That's what this z-score will have, and it's the exact z-score we want. It's exactly the z-score we want. So what this means is, at some point, we're going to want to get a z-table, which is exactly what we're going to do here. Allow me to share what I'm seeing. We're going to get into the z-table, and what we're looking for is 0.975 within the table, within the probabilities. And I think I spot it. There's 0.975. In fact, it's perfect. Normally, we can only get as close to it, or as close to 0.975 as we can, but this just so happens to be something we can get right up on. That's actually the nice thing about 95% confidence intervals, is that if you're talking about these kinds, then you're going to get a nice simple z-score of 1.96. 1.96. So for a 95% confidence interval, your z-score is going to be 1.96. In fact, that's going to be true for any z confidence interval in this course, which is really convenient, really nice to hear. Okay, so 1.96 is our z-score. So going back to the notes, that is what we're gonna put in here. 1.96. We're gonna use that trick a lot. So 1.96 is our z-score. This is a little cheat sheet for you. You know, you can reference it in your mind if you can memorize these. The most common confidence intervals you'll see are 90%, 95%, and then maybe 99%. Pretty much any statistician will know this one, the 1.96. They might know 1.645, but they'll definitely know this one. So if you have a 95% confidence interval and you're using a normal distribution, a z-score in your confidence interval, which is not always guaranteed, hardly. In fact, in the next section, we're going to see a different underlying distribution. But if you're doing a 95% Z confidence interval, your critical value, your Z-score, will be 1.96 that you use in the formula. If you're doing a 99% confidence interval, it'll be 2.575. And then this is the formula you're going to be using. This is our gold standard formula here. P hat plus or minus the Z-score. That alpha over 2 is a subscript on the Z-score times the standard deviation business. So, in a survey conducted by Princeton Survey Research Associates International, 800 randomly selected 16 to 17-year-olds were asked if they ever used their cell phone while driving. Of the 800 teenagers surveyed, 272 indicated that they text while driving. The other, what is that? The other 528 were lying, because we all know that all teenagers are constantly on their phones at every moment of every single day. And I really can't blame them, because that's probably also true of me, although I try not to do it when I'm driving. And by try, I mean I absolutely don't do it while driving. So I don't do it while driving, but come on, teenagers, we know they're always on their phones watching TikToks and doing Snapchat and all that business and whatnot. So construct a 90% confidence interval for the proportion of 16 to 17-year-olds who text while driving. 90% confidence interval, I get to use my little cheat sheet. If I'm doing a 90% confidence interval, the Z-score I'm going to be using is going to be 1.645. Okay, so let's do a bird's eye view here. Let's walk this out. P hat. So remember, here's our formula. Here's our formula. It's all the way back up here. We need to know what P hat is. That's just the sample proportion. That's easy. We need to know what the Z-score is. We've already found that from our little cheat sheet. We still know what P hat is, and then we just need to know N is the sample size, 800 in this case. So here we go. Let's rock and let's roll. P hat is going to be X over N. X is going to be the 272 who indicated that they text while driving, divided by 800, which is the sample size. X over N, that's all that means. So 272 divided by 800 will come out to exactly, without needing to round, 0.34, which is nice. The critical value, well, remember, for a 90% confidence interval, it's 1.645. It's hard to see now. That's why we wanted to look at it earlier. 1.645. I don't even have to think about it, because I do have that nice little cheat sheet. How very, very convenient. Let me pull all these up. Muy convenient. So now the confidence interval is going to be p hat plus or minus our z-score of interest times the square root of p hat times 1 minus p hat all over n. So that's going to be 0.34 plus or minus 1.96 times the square root of 0.34 times 1 minus 0.34, all that's still in a square root, divided by 800. Now at this stage of the game, you're going to have to be kind of a calculator super whiz. 0.34 times 1 minus 0.34 divided by 800. Then you can take the square root of that. Then you can multiply by 1.96. And you'll end up with a margin of error. So you'll have 0.34 plus or minus. Your margin of error will be, I'll round it to 3 decimal points, 0.033. So your margin of error is 0.033, also known as 3.3%. So remember what plus or minus means. We're going to go down 2 routes here. We're going to do 0.34 plus, I want to do a different color here, 0.34 plus 0.033 be 0.373. And then on the other end of that, 0.34 minus 0.033, 0.307. So here's the low end estimate, 0.307. Here's the high end estimate, 0.373. So unfortunately, we need to drag this down. We'll drag this up. So we are 95% confident that the population proportion of 16 to 17-year-olds who text while driving is between 0.307 and 0.373. So somewhere between about 30.7% and 37.3% of teenagers text while driving. Again, a lot of them are probably lying in that survey, but because we're all confident it's closer to 100%, but whatever. Another way, a better way to write and I'm just going to use CI, not confidential informant, but confidence interval. You can use interval notation, 0.307, comma, 0.373. If you remember your interval notation from algebra, put parentheses around it, the comma in between. We're in this case, 90% confidence that the population proportion falls between 0.307 and 0.373. That's all a confidence interval is. It's an interval estimate as opposed to a point estimate. So again, the hard part is getting the z-score. Once you know what the z-score is going to be, it's not so bad. This one, number 3 here, is going to be identical to the last one, with the exception that we're now constructing a 98% confidence interval. So we'd go up here and use a z-score for 98%, which is 2.33. So instead of the 1.645 we use, we're going to use 2.33. So just keep that in mind. Actually, never mind. Just keep that in mind. Now, one thing we can do is we can compute the necessary population size. Sorry, hold on. But let's compute another confidence interval real quick so we can get some more practice in. Let's see. Okay, here we go. This is what I want. I thought I had the right one queued up and then I accidentally X'd it. Okay, so let's look at this one. Compute the critical value, the z-score that corresponds to a 96% level of confidence. Let's do that one together. 96% is not on our little cheat sheet. So let's draw a picture of the normal distribution, bell-shaped curve. Between our two z-scores in the middle here, we want 96% of the data to fall. So that means, or remember, that can be seen as 0.96. That means we're leaving 1 minus 0.96 equals 0.04. We're leaving 4% on the table. So there's 4% that's going to fall within these two tails. We divide that in two to figure out how much will fall into each tail, and we see that's going to be 0.02. So 0.02 down there, 0.02 up here. Whatever this z-score is, let's say it's our target z-score. Oops. This is our target z-score. You'll notice it has 0.02 of the data to the right of it, which means it has a total of 0.98 of the data to the left of it. Of the data falls to the left of it. So ultimately what we're going to do is we're going to look for the z-score, or get as close to the z-score as we can, that has 0.98 of the data falling to the left of it. So keeping that in mind, we know it's going to have to be a positive z-score that does that. We're looking for 0.98 inside the table, or as close as we can get to it. Let's see, it looks like the closest we can get is 0.9798. 0.9803 goes just a little too far the other way. So 0.9798 is about as close to 0.98 as we can get. And that is a z-score of 2.05. 2.05. And that's going to be our answer here, 2.05. Boom. Not so bad. Pretty easy. Construct a 90% confidence interval for the population proportion using the given information. X is 75, N is 250. Okay, this one's not going to be so bad. Our formula is going to be P hat plus or minus the z-score times the square root of P hat times 1 minus P hat all over N. From our cheat sheet, we might recall that the z-score for a 90% confidence interval is 1.645. P hat is going to be the number of successes, 75, divided by 250. So 75 divided by 250 is going to be 0.3. So now let's construct the confidence interval. It's going to be 0.3 plus or minus the square root, the z-score of 1.645 times the square root of 0.3 times 1 minus 0.3, which is just 0.7, all over the sample size of 250. And so now I'm going to do the margin of error calculation. You can do 0.3 times 0.7 divided by 250. Then you can take the square root of that, then multiply by 1.645. You're going to end up with 0.3 plus or minus. If we round to, it wants us to round to 3 decimal places, so it's going to be 0.048. Then we go down the 2 paths. Yes, there are 2 paths you can go down, but in the long run, there's still time to change the road you're on. We want 0.3 plus 0.048. That's going to be 0.348. That one's easy. 0.3 minus 0.048 is going to be 0.252. And there we go. Our lower bound is 0.252. Our upper bound is 0.348. And that works. So we are 90% confident that the population proportion for whatever the heck this is measuring, I have no idea what this is measuring. It doesn't give you any details, any problem details. It's just like, here's X and here's N and the confidence level. But you can still calculate the confidence interval for whatever it's supposed to be. So for whatever this is, we are 90% confident that the true proportion falls somewhere between 0.252 up to 0.348. There's a few things you can do to make your confidence interval better. If you take a larger sample size, you're dividing by the sample size, so that's going to shrink the margin of error. And if the margin of error is smaller, you don't have to add as much or subtract as much, and your confidence interval is going to be less far apart. The upper and lower bound will be closer. So increasing your sample size decreases your margin of error. Just looking at the math, that's true. It also makes sense logically, because a better sample size is just better overall. So increasing sample size, all else held constant. Increasing sample size decreases margin of error, making the interval smaller, or sometimes they use the word narrower. That's going to be an important effect. In fact, the sample size has so much bearing on the confidence interval, on the margin of error and how wide the confidence interval is going to be, that the sample size is something we can be interested in figuring out. how large a sample size do I need to get this margin of error to be this accurate? Well, that's what this little beauty is going to be here. It looks bad. We're going to figure out the sample size necessary for estimating a population proportion with a specified margin of error. So if you have a certain margin of error in mind that you would like to end up with, well, all we did technically was we solved the margin of error problem, but we solved it for n. We set it equal to that. So you can, figure that calculation out for yourself. It's p hat times 1 minus p hat times the z-score divided by the margin of error, then squared. So only this part's squared. So yeah, that's just a new formula we're throwing at you. But let's think about it. Before we go in and take the sample and calculate the confidence interval, we would like to know what this is. We would like to try and figure out what sample size we need. So we haven't even done anything. So how can we calculate p hat, which is the sample proportion, if we haven't even gone and collected a sample yet because we're trying to figure out how large a sample we need? That creates a problem for us. So there's two solutions to this. Your one solution is to use an estimate of p hat based on a pilot study or an earlier study. So what you're trying to do is make a confidence interval for p hat, but you don't know p hat until you collect a sample, but you can't collect the sample until you have a sample size, which is what you're trying to calculate. So you're just going to need to use an estimate of p hat in this formula here. If you don't have a prior estimate, it said, let p hat be 0.5. That's what we're going to end up doing. So I either have a prior estimate for it, which is either the problem's either going to give you a prior estimate. If the problem doesn't give you a prior estimate, assume a p hat of 0.5 when you're doing this computation. In a final analysis. So a sociologist wanted to determine the percentage of residents of America that only speak English at home. What sample size should be obtained if she wishes her estimate to be within 3 percentage points with 95% confidence, assuming she uses the 2000 estimate from the Census Supplementary Survey of 82.4%. Whoa, Nelly. Let's get everything, let's put all our cards on the table. We're doing a sample size calculation. I'll go ahead and put the formula up here. It's, just have to write it out. N equals p hat times 1 minus p hat times our z-score of interest divided by the margin of error squared. And we'll double check that, but that is correct. Let's just write out what all of our variables are here. N is what we don't know, the sample size. We're trying to figure out what sample size we should use. P hat, we're going to use the prior information, 82.4%, which is 0.824. The z-score of interest, since we're talking about making a 95% confidence interval, the z-score is automatically going to be 1.96. And then E, the margin of error, it wants to be within 3 percentage points. So the margin is 3% or 0.03 expressed as a decimal. So then the sample size needed is going to be 0.824 times 1 minus 0.824 times, in parentheses, 1.96 divided by 0.03 quantity squared. And only 1.96 over 0.03 is squared. So we can do this computation. Technically, you can do it all in your calculator if you're savvy with that. If that's your fancy, I'm doing it right now. And I'm getting about 619.03. But normally what you want to do is you want to round up. Because when it comes to sample size, you usually want to get as large a one as you can. If you're going to get a value that's not a whole number here, round up to the next one so you're being conservative. You're going larger. You don't just round to the nearest, you round up. So what we want is 620 in our sample size here. All right, not so bad, 620. If we don't have a prior study, if we don't have a prior sample size or the p-hat that we can use, we're going to use a p-hat of 0.5. The reason is that technically you have to use calculus to prove this, but the reason is that actually will yield us the largest sample size possible. So being conservative, we use a p-hat of 0.5 so that we know we will capture a margin of error that we want. So that finishes off section 9.1. What we're going to see is that in section 9.2, we're going to just be constructing confidence intervals, but now for a different underlying parameter. So in section 9.1, we were calculating a confidence interval for a population proportion, Now what we're going to talk about is calculating a confidence interval for a population mean, which is mu. So we're looking at a completely different parameter here. And a proportion is nice, but a mean is kind of more likely what you would be doing statistical inference on if we're just being completely honest with ourselves. And we should always be honest with ourselves. So remember, we started this at the beginning of the last section. That was 2 weeks ago now. But a point estimate is a value of a statistic that estimates a parameter. So a point estimate is just a single statistic that's used to estimate the value of a parameter. So if you have these 10 things, these are brain volumes in centimeters cubed of subjects used in the study. We would want to, of these 10 things, we would want to take their average. So 963 plus 1027 plus 1272 plus 1079 plus 1070 plus 1173 plus 1067 plus 1347 plus 1100 plus 1204. And then there are 10 things, so we divide by 10. We're going to get X bar 1,130.2 centimeters cubed. So the average of these 10 brain volumes, which is something I've never thought to calculate before, is 1,130.2. This is just the average of 10 brain volumes. Does that mean the average person living in the world today has a brain volume of 1,130.2 cubic centimeters? No, this is just the average of our 10 sample points. We're using that as a point estimate for the population, but I have no idea how good of an estimate that is. So what we'd rather have is a confidence interval. I would much rather have a confidence interval. So instead of saying the average person's brain is 1,130.2 cubic centimeters in volume, instead of saying that, I don't know how good of an estimate that is. I only had 10 brains. Maybe I got them all from just one country, and maybe brain sizes differ among countries based on, I don't know, their wealth and their economics and, you know, how well nourished they are. That might change the volume of a person's brain. So if I can't make that claim about all of humanity. So I'd rather have a confidence interval for different reasons to give up the idea that, well, there's like a range of values here. There's a nice range to them. So we're going to have our own confidence interval formula now, but it's for the population mean. Earlier, it was for the population proportion. And remember, that one was p hat plus or minus the z-score times the square root of p hat times 1 minus p hat over n. This one looks simpler. This one looks simpler. You're using your point estimate like p hat, doing plus or minus all the same. This here is the margin of error. So margin of error is everything after the plus or minus. But wait a minute, let's zoom in here. Instead of having a z-score, we have something called a t-score. What is it? We have something called a t-score. Well, the z-score was associated with something called the normal distribution. But a t-score is associated with a completely new distribution called the t-distribution. The t-distribution. We have to use it when we have a very small sample size. We must use it when we have a very small sample size. Why? Why do we have to do that? Well, remember, we had something called the central limit theorem. We didn't talk in horribly much detail about it, but the central limit theorem, basically, here's what's happening. If you know you're pulling data from a normal population, a population that is normally distributed, you can automatically construct a confidence interval that involves z-scores. But we rarely will ever know that. We will rarely ever have that case where we're pulling from a normal distribution. So instead, we just pull from any population. So notice it doesn't say it's taken from a normal population. It just says a population, where we don't know what the population it came from looks like. We have no idea. So if we had a large enough sample size, if we had a sample size of at least 30, well, then something called the central limit theorem kicks in. And even though I don't know my population came from the normal distribution, I can still use a z-score in my confidence interval and in my calculations. So this gives us a nice little system. Our system. If we know our data, our population is normal. That is, if we know the population we are pulling from is normally distributed, we can use z-scores. We can use confidence intervals. We can calculate probabilities in Chapter 8 using z-scores. Also, if we don't know the distribution of our population, well, I should say however is a better word for it. However, if we don't know the distribution of our population, like in this first case here, if we don't know the distribution of our population, but we get a sufficiently large sample size, and they usually say n more than 30, n greater than or equal to 30. So as long as you get a large enough sample size of maybe at least 30, we can still use z-scores. Yay, we can use z-scores to calculate probabilities. We can use z-scores to construct confidence intervals. And then in chapter 10, we'll see we can use the z-score hypothesis test with a z-test statistic. But there's a little problem. There's a little problem. If neither of the two conditions above apply, that is, if you don't know the population distribution and you have a small sample size, you must use a new distribution called the t-distribution. This means you will be using t-scores, not z-scores anymore. So we have to completely reframe our concept here. Small sample size and you don't know the distribution of the population, you have to use the t-distribution, this brand new distribution that we're going to use here today. It's also called, as you see here, the student's t-distribution, the student's t-distribution. Now, we're not actually going to use this formula here. This is just an interesting little thing that basically defines the t-distribution. We are going to use something called degrees of freedom. And without going into uber detail about that, the degrees of freedom is just going to be your sample size minus 1. So whatever the sample size you're dealing with is, take 1 off of that, and that's what's called your degrees of freedom. You're going to use the degrees of freedom to look up t-scores on the t-score chart. Just like we have a z-chart, we also need to have a t-chart for similar reasons. But I think for the last thing we'll talk about today is a neat history lesson, the student's t-distribution. A neat little history lesson on it. This distribution was developed by a statistician, aka quality control, a quality control employee of the Guinness Brewery. And when I say Guinness Brewery, I'm not talking about some, cute little pop drink. I'm talking about beer. I'm talking about Guinness beer that I'm sure most of you have heard of it before. It's served at many, many bars. It's a stout, dark beer. It's pretty good if you like dark beer. I don't know what your personal tastes are, but most bars will probably have Guinness, especially if you go up to the Northeast. If you go to Boston, Guinness is real popular up there, I think. But yeah, dead serious. The Guinness Brewery out of Ireland, although I believe this was developed in America in one of their American breweries. It was developed by a statistician who was trying to do statistical inference to get the quality of the beer to be consistent. Because think about it. If you have a Guinness beer and you buy a 6-pack of it, you want each one of those 6-packs, each drink, or each of the beers in the 6-pack to taste basically the same. You don't want to get one that's real funky and it's too light. And when you're looking for a nice dark beer, you don't want to get one that's too sweet. You don't want one that's too sour. You don't want one that's too hoppy, because you want to get the right balance of the hops and barley and everything that goes into making beer. So this statistician working for Guinness Brewery wanted to get the quality of the beer under control. But the problem is, whenever you're doing statistical inference, it's extremely expensive to get a large sample size. Because think about it, what the statistician would do would be to take 10 batches of Guinness beer and to test and make sure that all of the elements of it, the right balance of barley and hops are in there, the color is right, the taste is right. You can't afford to do a sample of 50 different batches of it. Because think about it, that thing takes forever to brew. Think about the giant vats they have there. And you want to run this test multiple times on multiple samples. You can't afford to do a sample size of 50 and do that 10 times. That could take months, and it would be extremely expensive. And your entire brewery is devoted not to actually producing beer, but to, quality control. So you need to use a smaller sample size. So this statistician realized that and developed an entirely new statistical concept called the t-distribution in order to still be able to do good statistical inference with small sample sizes. That's huge. Even though it started off at something like Guinness, which you wouldn't think would be as important as like medical research, it turns out that this concept had a huge rippling effect in statistics and completely, I would say, almost revolutionized a lot of the methods and procedures we're able to do in all of statistics, which affected all research that involves statistics, which hint, hint, wink, wink, is like all research today. Pretty much all research done in this world today uses statistics in some way. Can you imagine doing research and not involving numbers somehow? It just sounds silly. So this was developed. However, Guinness Brewery, they realized they were sitting on this amazing thing. They're like, wait, someone just like revolutionized statistics while working for us? Well, we don't want other beer companies, other breweries to have our secrets and make their product better using the secrets we developed at our own place, paying this guy out of our own pocket. So the statistician was not allowed to publish his research under his own name because then he'd get sued by Guinness. He probably signed a non-disclosure agreement with them. So he published it under the name Student. He used the pseudonym Student. And so we call it the Student's t-distribution to this day. So really interesting that it started out of Guinness Brewery. That's something that's really cool. So beer helped change the world. Okay, so that's going to be it for today. Let's take attendance real quick.